Welcome back. This is Professor Dorothy Hodgkin. She's a famous female chemist. She was the first British woman to win the famous Nobel Prize for Chemistry back in 1964, and her work included research into protein crystallography and the structures for vitamin B12 and the antibiotic penicillin. So groundbreaking research at the time. Now, what we're going to learn in this lesson is how we can communicate like a chemist or like Professor Dorothy Hodgkin so that other people can read our work. So the topic is communicating like a chemist. Okay, so the study design dot point, we're looking at chemical terminology, representations and conventions, which are really important not only in your scientific poster, but in all the prac work that you do. And when you're writing tests or exams or SACs, you want to use these representations throughout because they're part of the language of chemistry. Here we're looking at the report stage of the investigation cycle, which is the whole of the scientific report or poster. So we need to ensure that we're being as technical as we can be. So there's lots of things we're going to run through, which you can use like a checklist if you like. So first of all, chemical terminology. You need to use the chemical terms correctly in your communication. And you might be, or you should be familiar with a lot of these words, but you might not know the exact meaning. So it's important to just check that you're using them correctly. So an anion is a negatively charged ion. Examples include fluoride ion, sulfide ion, and carbonate ion. Atoms are the smallest unit of an element and they're uncharged. So they have the same number of electrons as protons. And we just use chemical symbols, element symbols, to represent atoms. A cation is a positively charged ion, such as potassium ion or copper 2 plus ion. A compound consists of two or more elements that are chemically combined. And they often have a chemical formula, such as carbon dioxide or potassium bromide. An element is a substance where the atoms have the same number of protons and therefore the same atomic number. And examples include potassium, which we've written as a name there. We could use the symbol, fluorine, capital F as the symbol, and lead, Pb. Okay. An ion can be an anion or a cation, and it's an atom or group of atoms that have lost or gained electrons and therefore have a charge. Examples being sodium ion and chloride ion. A molecule is two or more non-metal atoms that are covalently bonded. So sodium chloride is not a molecule. It's a compound, but not a molecule. Molecules include carbon dioxide and methane. A particle could be a proton, a neutron, an electron, an atom, or a molecule. It just means a small part. And a substance could be an element or a compound. But be careful about the words compound and molecule, which are frequently misused. So molecule only refers to nonmetals, whereas a compound can include ionic compounds that contain both metal and nonmetal ions. Okay, some key conventions. We use symbols to represent elements and use the periodic table to help you with this. For an example, the symbol for copper is Cu. Now, if you're looking at the symbols, the first letter is always capitalized, and if there is a second letter in the element, such as in Cu, the second letter is always in lowercase. That way, when you start putting atoms together in a compound, you can see where one atom starts and another begins. Superscripts are the high up values or symbols, and they're used to indicate the charge on an ion. Subscripts, like the 3 here, the 4 and the 2, are used to indicate how many atoms or groups of atoms are in a chemical formula. When we're naming and writing ionic compounds, we always put the cation before the anion. So the cation is calcium. So in calcium phosphate, we name it calcium phosphate with calcium first. And when we write the formula, we write the cation before the anion. Now, in Year 12, VCA penalise misspelling of chemical names. So you can lose a mark for not getting the correct spelling. To help you with this, use the periodic table to help the spelling of keywords, such as like fluorine is often misspelt. There is one exception though. Sulfur, we normally write with an F, but having PH is an acceptable alternative spelling for anything like sulfur or sulfates. Use the lower case for the first letter of a chemical element, unless it's the first word of a sentence. So if you're talking about oxygen, just use a lowercase, don't use a capital, unless it's the first word of a sentence. When you're naming transition metals that have multiple electrovalency, so the D block, write the name of the ion followed by a Roman numeral in brackets, such as Fe brackets 2 close brackets. And in organic chemistry, occasionally we use brackets in condensed and semi-structural formula, and this helps abbreviate the formulas there. Other conventions, an arrow indicates change, so it tells you some sort of change has occurred. We put the reactants on the left and the products on the right. And when we are balancing equations, we only change the coefficients, not subscripts. And something you can remember whenever you're writing equations or you're doing some stoichiometry is remember the acronym SUBS, which stands for check your significant figures, make sure you include units, make sure your equations are balanced, and include states where appropriate. Okay, some conventions with representations. There's lots of different types of formulas. So choose an appropriate formula type and underline that when you're answering a question, because if the question asks you for a skeletal formula and you supply a structural formula, you'll be incorrect. So some typical examples. Empirical formula is the simplest ratio of elements of different atoms in a compound, and it's derived experimentally. That's where the word empirical comes from. But it doesn't always show the actual number of atoms of each type. Molecular formula, if we multiply CH2O by 2, we get the molecular formula C2H4O2, and that gives the actual number and type of atom in the molecule, but it doesn't show you how those atoms are arranged. So molecular formula gives you the actual number of atoms of each type in the molecule, I should say. The structural formula shows how each atom is bonded to another, shows the bonding arrangement of the atoms in the molecule. But because this is drawn on paper, it's actually two-dimensional, and we're not showing, one of the problems is it's not showing the three-dimensional arrangement, which we could use if we used a ball and stick model or some sort of other model. Condensed formula is a way of summarising the structural formula, counting the first carbon and saying it's connected to 3 hydrogens, so that's the CH3, then another carbon with the carboxyl group, the COOH. So it shows where atoms are connected, and it shows which bonds atoms are involved in bonds, but it doesn't show the three-dimensional arrangement. Skeletal formula is quite common, and it shows the overall shape of a molecule, but it leaves out lots of information. And that can be useful if you've got a really large molecule rather than showing all the carbons and hydrogens. The carbons are implied by the vertices, and hydrogens are implied because it's assumed that all the other atoms that aren't listed are hydrogen, and each carbon can have 4 atoms. Okay, we also have electron dot diagrams that show bonding pairs and lone pairs of electrons. It only shows the valence electrons, not the inner electrons, and again, it's a two-dimensional representation. Ball and stick models have the advantage that they show things in 3 dimensions, and they show the ratio of the atoms according to the molecular formula, but the relative size of the atoms, the colour symbols, which we tend to use these colours, hydrogen white, carbon black, oxygen red, and nitrogen blue, they're not the actual colours of the atoms, and the distances between the atoms might not be accurate, and the angles. A space-filling model has the advantage that shows the overlap when sharing electrons in covalent bonds, but a limitation, it doesn't show the relative size of atoms. The angle of bonds might not be accurate. And the elements that are used where we use this sort of universal colour scheme can be useful when you're looking at a model. You know that the black one is carbon, the white is hydrogen, the red is oxygen. That can be handy in interpreting, but the atoms don't actually have those colours. Some standard abbreviations. Remember that they are case sensitive. Unfortunately, chemists are pretty lazy with their symbols, and they tend to use similar letters: T for temperature and time, N for number of mole, number of particles, Avogadro's number. So it's important to get the lower or uppercase right. But the amount of substance in mole, abbreviation N, number of particles, capital N. Now, when you're typing and using something digitally, put your abbreviations in italics. Obviously, you can't do that when you're writing, so don't worry about when you're handwriting. Avogadro's number, capital N, subscript, capital A, not to be confused with sodium. Mass, small m, molar mass in grams per mole, capital M. Relative formula mass or relative molecular mass, capital M, subscript little r. Relative atomic mass, A, subscript little r. Relative isotopic mass, I, subscript little r. Specific heat capacity, little c. Volume, capital V. Concentration, C. Concentration in molarity, square brackets. Molarity, capital M, which of course is the same as molar mass, so context is important for that. Pressure is P. Temperature is capital T. The gas constant is R. Time is small t. Percentage, you know the symbol for that. And capital delta is our symbol for change. So units of measurement, we think back to the acronym SUBS that we talked about. U stands for units, and always make sure that you include relevant units. So if we're looking at small n, we're talking about mole. If we're looking at mass, small m, we're talking about grams. If we're talking about molar mass, we're talking about grams per mole. All the relative atomic masses, isotopic masses, formula masses, molecular masses have that subscript R, so there's no units. They're relative to one atom of 12 carbon exactly. Volume is in litres. Pressure, the standard unit is kilopascals, but there are units conversions in the data book. Concentration in molarity, which is capital M in mole per litre or molarity. Concentration in other units, such as grams per litre. It's really important if you use concentration in other units to specify the type of concentration unit so that the reader understands what you're talking about. Molar volume, which is V subscript M, is litres per mole. Temperature, the standard unit is Kelvin, but we do use temperature in degrees Celsius in the laboratory. And density, which is sometimes written as D or sometimes you'll see it as rho, is grams per mil or kilograms per litre, and the units depend on what you've got in the stem of your question. The key unit conversions here, you find these in your data book. So to convert degrees Celsius to Kelvin, kilopascals to millimetres of mercury, atmospheres or bar, and some volume conversions as well. Also in your data book, so you don't need to remember it, are some really handy metric conversions. So most of the time in the metric system, things change in multiples of 1,000. So we go from 10 to the 3 to 10 to the 6 to 10 to the 9, or 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the minus 12. Then we have a couple of commonly used units. We know centimetres, 100 centimetres is 0.1 of a metre. So the prefix centi means 100 or hundredth. The other common unit that's particularly used in Europe is deci. Whether you're talking about the SI prefixes, make sure you get uppercase or lowercase correct. So giga, like in gigabytes of memory, is capital G. Mega is capital M. Kilo is lowercase k. Milli is small m. To distinguish it from micro, which is a mu, which is a Greek letter. Nano is small n, and small p is pico. Often we use algebraic equations or mathematical equations in our data processing, and a lot of the equations are given to you in the data book. One that's often not in the data book is the density equation and also the relative atomic mass formula. So they're useful formulas to memorize if they're not already in your data book. So here we have a mega question activity. A student wrote the following sentence in their logbook about the method they used in the experiment. Read that and answer the question. Okay, this is not the best sentence that someone's written in their report. For a start, they're referring to themselves, I mixed, but we'll look at the actual technical problems with it. I mixed a molecule of sulfate copper. That's not the way we name ionic compounds. We always name the cation before the anion. So we would say that it's copper, sulfate, but we can have CuSO4, which is copper 2 sulfate, and we can have Cu2SO4, which is copper 1 sulfate. So I assume here we're talking about copper 2 sulfate, so we need those Roman numerals in there as well, with magnesium ribbon and this substance, which looks like a combination of magnesium and manganese. Now, remember spelling is really important in chemistry. So that should be magnesium, and you can use the periodic table to help you with the spelling. Okay, it also talks about a molecule. Now, we can't measure one molecule, but molecules refer to non-metal substances, and copper is a metal. So it wouldn't be a molecule, it could be a compound. So we've got the molecules wrong. The sulfate copper has 2 mistakes with it. The magnesium sulfate is a mistake. So there are 4 errors in this sentence. And it's not the best worded sentence anyway. Okay, so to summarise, when communicating your ideas in chemistry, it's important that you use appropriate terminology, representations and conventions. This occurs throughout chemistry. So whether or not it's with your key science skills or your unit area of study 3, this happens in exams as well. So you need to know how to communicate chemical terminology, naming, equations, representations, standard abbreviations, units of measurement, metric prefixes, and algebraic equations. So you could make this into a little checklist, if you like, of things to remember. What's coming next? We're going to analyse, evaluate, and communicate scientific ideas, part 1. I'll see you then. Bye.